All right, welcome everyone to this week's Autonomy Talk. This week is a great pleasure to have with us Professor Filipe Rodrigues, who is an associate professor at the Technical University of Denmark, aka DTU, and he works in the Machine Learning for Smart Mobility Lab. So something about Filipe, he holds a PhD from the University of Coimbra in Portugal, where he was working on probabilistic models for learning from crowdsourced data. And previously, he was a postdoctoral fellow at DTU with a very hard to pronounce fellowship, which I will only pronounce the acronym, which is COFUND. And there he used to work on spatiotemporal models for mobility demand. So the primary goal of his research lab is to use machine learning for understanding and optimizing urban mobility and human behavior. He's been very successful in this area. As you've seen in the bio, is published many articles both in transportation and machine learning. And today, we are very excited to hear a talk titled Reinforcement Learning for Network Optimization in Transportation. This is very exciting work because it's bringing some of the standard algorithms to scale with the real life challenges and real world applications. And I'm personally very excited to hear more about it. And I give you the stage, Filipe. Thanks again for coming.
Thank you, Joel, for the introduction. Thank you very much one more time for the invitation. Yeah, so I'll be talking about reinforcement learning for network optimization problems in transportation. So the motivation for these comes from the fact that several problems, not only in transportation, actually some of the things that I'll talk about can actually generalize to other application domains, but several problems in transportation can naturally be posed as graph structured Markov decision processes. So if you think about any problem essentially where you're trying to control flows or products or vehicles or other quantities on graph structured environments, so things like vehicle routing, fleet management, so trying to do supply chain, other logistics problems, or if you're just trying to do power grid management, essentially you have a graph structured MDP where you're trying to make decisions on top of a graph. And these network optimization problems have been extensively studied in the literature. However, I would argue that traditional approaches do not scale very well to large networks because very often they tend to rely, for example, on things like time expansion techniques. And when you start basically to have to take the temporal dimension into account, then the complexity of these problems that quickly starts to explode. The other thing is that the representation power of these approaches is rather limited, so they tend to rely on linear approximations to stochastic and nonlinear systems. And this also creates some challenges. You can go with approaches based on heuristics, but often the design of good heuristics for this requires a lot or significant manual trial and error. So what I will try to argue is that reinforcement learning can help address the open challenges in this space by providing, for example, extremely scalable inference. Once the algorithms the policies are trained, we can deploy them, and inference is very scalable and fast. These RL-based approaches can handle complex dynamics, complex observations, and so on, and they essentially provide us a way of doing data-driven policy discovery. So they have a lot of things going for them. However, there are also some challenges in trying to do, let's say, end-to-end reinforcement learning on these problems. So here we assume that we have some state, and the state is defined over a graph. So we have, for example, node features as well as edge features. And the end-to-end reinforcement learning problem that we'll be trying to solve is to have some reinforcement learning agent that will take this state and try to output actions over the graph. And these, for example, will be movements of quantities along the edges. So we'd say, for example, take 5 vehicles from this node to this other node, where nodes could be representing areas. I'll give a concrete example in the next slide. But this is challenging for two main reasons. First of all, this requires specifying distribution over actions, and this distribution will be over all elements in the graph, like, for example, all the edges. And this leads to essentially an extremely large action space, which creates a lot of challenges for learning. The other problem is that ensuring that the action is valid can be quite difficult. So very often we have domain constraints. For example, if you're trying to think of sending 5 vehicles from this area, this node to this node, then this is only possible if we have more than 5 vehicles here, of course. And very often ensuring these domain constraints can be challenging. So to try to overcome these problems, we proposed what we call a graph bi-level reinforcement learning framework. So in this bi-level approach, rather than having the reinforcement learning agent decide, take an action directly on the graph, we instead have the reinforcement learning agent deciding the desired next state. And then, based on the desired next state that the reinforcement agent outputs, we then solve an optimization problem, in this case, a linear control program, to try to achieve the desired state. And of course, we try to achieve it as best as possible. So of course, it might not be possible to achieve that exact state, but we try we optimize to try to match it as best as possible. So these often translates to solving a linear control program where we're essentially trying to minimize or finding the, let's say, the low level action in the low level controller that matches as best as possible the desired state. And here we can actually easily ensure or introduce domain constraints. So things like on conservation of flow or network flows, things, another constraints that we may have. So let's see what a concrete example of this, concrete instantiation of this framework can look like. And before that, let me just mention, yes, that why graph-based RL? Well, we are essentially solving a graph-based MDP, so it makes sense to try to use graph reinforcement, graph neural networks to represent our policies that we try to learn. And this is actually something that we found. In particular, we found that message passing type of graph neural networks tend to work very well, particularly well, for solving these sort of problems. Because essentially what they provide is with the right inductive biases that fit well, at least on our experience, that fit well this problem. So let's then look at the concrete instantiation of this framework. Let's consider the problem of fleet management, where we essentially have our city. We have a fleet in our city, and our city is partitioned in different zones. So we represent each zone of the city as a node in the graph. And here we are essentially trying to determine how to rebalance vehicles from one part of the city to the other in order to try to essentially anticipate future upcoming demand and essentially managing the fleet optimizing the supply distribution to try to anticipate or accommodate and anticipate upcoming demand. So in this bi-level framework, solving this problem it will be something like this. So we will have a graph-based reinforcement learning agent, and this graph-based RL agent will essentially determine the desired next state, and this, in this particular case, will be the desired distribution of idle vehicles. So it will be saying like, okay, I would like to have in the next time step, I would like to have 10% of my vehicles in this area of the city, 20% of my vehicles in this other area, and so on. So it's essentially outputting a probability distribution over the different nodes. And the critical advantage here is that the number of nodes is, of course, much smaller than the number of edges, right? So if we were to do end-to-end RL, we will have to determine specifically how many vehicles we should reposition at every time step between the different zones. So that will be essentially n squared action space, while here we are dealing with a much smaller action space, which is just the number of nodes. And then in the, let's say, the lower level controller or in this bi-level framework, what we will do is to try to convert the desired distribution of vehicles that the RL agent outputted into an actionable rebalancing flows. And to do this, we essentially just solve a minimum rebalancing flows problem to try to best achieve the desired distribution of vehicles. So this second part of this lower level control is essentially saying, well, the first part, the upper level control, is saying I would like to have 10% of my vehicles in this part of the city, 20% in this other part, and so on. And then the lower level controller will be deciding where the vehicles should actually come from in order to try to match this desired distribution, of course, obviously minimizing rebalancing costs. So the two key advantages is essentially that the action space of the R agent is now much smaller. The second key advantage is that by solving minimum rebalancing flows, we can easily introduce constraints. So domain constraints are naturally integrated in this framework. So what this bi-level approach is essentially doing is trying to combine the best of both worlds between learning-based control and optimization methods, right? So we have, and essentially trying to leverage the advantage of having optimization methods that are very efficient at solving this problem in one time step, so without accounting for the temporal component, and they don't require any training. They easily ensure domain constraints with the advantages of learning-based control, which is the ability of doing things data-driven, handling stochastic environments, and also the scalability, as I will show in some of the results later on. So this is essentially the general idea. So here, I'm showing some results for this approach applying for an AMOD rebalancing problem. So here we essentially have the city partitioned in different areas. We have our graph over the city. And so the upper level controller is the RL agent deciding the distribution of vehicles, as I mentioned, and then solving the linear control program to find the rebalancing flows. And I'm showing results here in terms, so this is showing rewards. And rewards are essentially profits, revenue minus the rebalancing costs. And here we are comparing our proposed approach with end-to-end reinforcement learning. And as we can see, while end-to-end reinforcement learning really struggles to find a good solution, our proposed graph-based bi-level approach works much better. And we even compared it with what we call an oracle. And for us, this oracle is a model predictive control solution, which actually has perfect foresight. So it knows about the future upcoming demand, the exact upcoming demand. So it's able to solve the problem exactly. And as we can see from the results, actually, we're able to get quite close to the oracle. So we even compared with some random baseline and also with some heuristics approach. And we essentially saw that our proposed approach outperforms both end-to-end RL and the heuristics, and we're able to achieve near optimal or near oracle performance. But crucially, unlike the oracle, what we saw is that our bi-level RL framework is able to scale much better to large networks. So here, as we can see, that as we increase the dimensionality of the network, while the MPC approach, the multiplicative control, the Oracle starts to really explode in the complexity, we see that our proposed approach scales much better. So then we started exploring this framework for other problems. Another one that we saw was for supply chain management. So here we are essentially trying to determine how much inventory we should send across the different warehouses and things like that. And here, similarly to the previous approach, the RL agent decides the desired distributions of the inventory. And then we solve a linear control program to figure out where that inventory should come from. But that's, of course, just in one time step. So that's not accounting for the temporal component. The idea is that the RL takes care of the temporal component of the problem. And the results are similar to the previous slides. So we can see that our proposed approach is able to achieve near Oracle performance and is clearly outperforms or substantially outperforms both end-to-end RL, trying to do end-to-end RL, either with MLPs or with GNNs. And it also outperforms domain-driven heuristics. And one interesting thing that we saw is that actually, if we look at the previous slide, these policies not only have this ability of being close to the Oracle performance. One nice thing that we were already seeing in the beginning was that by using the inductive biases of graph neural networks, we saw that they were generalizing very well across cities. So here we tried zero shot, just learning one control agent in one city and deploying in another city. And then we saw that just this zero shot performance was already quite good, and the agent was performing not very far from the agent that was trained specifically for that city, for example. So we were observing already very good zero shot generalization, and most importantly, again, was the fact that this is able to scale much better to large networks. But motivated by this zero shot performance that we were starting to see already in the beginning, we started to see, okay, can we do even better? And one idea that we had was, let's try to use meta learning for fast adaptation. So as a motivation example, why this is relevant. So if you think of the AMOD control problem, where you're trying to rebalance your fleet of autonomous vehicles in the city, it doesn't make sense that you as the controller tries to learn one control agent from each city from scratch every time, right? You probably, if you are an AMOD operator, you may have agents or you may have vehicles deployed in different cities. So can you learn from these multiple cities and try to, rather than retraining for every city, reuse the previous experience? So we essentially propose the use of Meta RL to do this. And Meta RL essentially provides us with the mathematical formalism for fast adaptation to unseen scenario. So the idea of essentially learning to learn. And I'm not going to go very much in the details of how the approach works. We use something that is called Meta RL through recursion. And using this approach, what we did was to essentially we constructed a meta training set consisting of data from multiple cities. So these are the environments, the training environments that we had in our training set. And then the idea is that we have a reinforcement learning agent interacting with these different simulation environments and using this meta reinforcement learning through recursion approach to then learn an agent that we can then deploy in the meta test set, which in this case consists of this three different cities. So what we saw again was that our previous approach is, if we just zero-shot transferred it to a new city, it was already performing relatively well. In most cases, maybe better than the domain-driven heuristic. So this is an equal distribution heuristic. Then we saw that if we fine-tune this zero-shot approach a little bit, so we let the agent learn a little bit, interact just a little with the testing environment, and then we saw it was quickly adapting, so it was performing even better. But then what we saw is that using meta reinforcement learning, we were able to um, generalize much better to unseen cities. So here we can see that we are getting close to this single city column represents the agent that was trained specifically from that city, so from scratch, but trained just on data on the environment from that city. And we saw that the meta learning agent that never saw this city before could actually perform as good, or in some cases even outperform the agent that was trained specifically from that city. And in both cases, we see that we are very close to the Oracle model predictive control approach, which is of course exact but doesn't scale very well. And this is the MPC, but using forecasts. So this one is using perfect foresight. This one is using forecasts of the future demand. So in general, we saw that this graph based RL with meta reinforcement learning was getting close to optimal performance in cities. And crucially, we saw essentially a huge gain in terms of sample efficiency, because of course we don't have to retrain from scratch every time we try to deploy the controller policy in a new city. So then we started to see, okay, these policies are actually quite generalizable. So they tend to generalize well to new cities. So they seem to be very robust. And then we tried to push it to see how robust these policies that we were learning with this meta reinforcement learning approach, how robust they really were. And we started considering scenarios. So things like, for example, special events, extreme congestion scenarios, and changes in the pricing scheme, for example. So changes in the reward structure. So we essentially try to test these learned approaches in out-of distribution. And here, for example, we can see some results for this event scenario where we basically have one part of the city, one area of the city suddenly having a huge peak in the demand. So trying to sort of simulate the presence of a special event that was driving a lot of demand for that area. And we again saw that the meta learning based approach was much more robust to this sort of, let's say, disturbances. And then we started thinking, well, but maybe manual rebalancing of vehicles is not the only way we can achieve a more balanced distribution of the supply. So perhaps another approach, or certainly another approach, is to use pricing as an incentive or disincentive to try to achieve a more balanced distribution. So if a lot of vehicles are getting stuck in one area of the city, we can try, for example, to lower the price to encourage people to take those vehicles from that area to perhaps other areas of the city. So we can use pricing. And here our idea was essentially, well, can these two control strategies, let's say, work in tandem to achieve a better balance? So we essentially extended our previous approach to, well, first of all, we changed the environment to be now price sensitive, so that the demand reacts to the price that we set. And then we extended the previous approach, bi-level approach, so it's still a bi-level approach. But here, rather than having the reinforcement learning agent just determine the desired distribution of the vehicles across the different areas of the city, so the graph neural network essentially has one extra output that is outputting the price of the trips that start in that origin. So actually a multiplying factor for the price for trips that start in that area. And what we saw was, well, unsurprisingly, we saw that the rebalancing, jointly rebalancing and pricing led to higher rewards, which this was not really that surprising. But for me, at least, more interesting was the fact that the learned policies were essentially trying to find a trade-off between these two strategies. And it was interesting for us to see when the reinforcement learning agent was deciding to try to, for example, lower the price to try to encourage people to take trips and take the vehicles out of that area, versus when it was deciding, okay, it's useless, it's pointless trying to lower the price here. It's more effective just to manually rebalance the vehicles directly. So it was interesting to see how the policy was handling this trade-off. And the other interesting fact that we observed was that how much better, how much improvement we were able to see from the joint approach of rebalancing and pricing was highly dependent on the scenario that we were considering. So we used data from different cities. So we constructed different scenarios, and depending on the scenario, on the characteristics of the scenario, we saw rather different results. Okay, so this is, so far we've been discussing this bi-level framework, its advantages, and so far we've been relying on the use of simulation, some sort of simulation environment for training the reinforcement learning agents. But this actually can be quite challenging and costly. Developing and calibrating complex urban simulation environments from scratch, it can be quite challenging and as I mentioned, costly. And then on top of it, you need to have extensive interaction. You can need to let your RL agent interact with this environment for many iterations for it to learn. And then once you've learned that agent, you still have, and when you reach the deployment time, you still face some sim to real distribution shift challenges. So in most cases, actually, we do have a lot of historical data from previous operations. So if we think about the case of autonomous mobility on demand, for example, again, or let's say your Uber or your bike sharing operator, based on whatever current policy you're currently using to rebalance or manage your fleet, this may be an heuristic or some optimization method, whatever this current policy you're currently using, these operators already have quite a lot of data, historical data that you can use. So the idea here is that, well, can we try and learn a control policy bi-level, ideally, because we saw the advantages of bi-level approaches? Can we learn a bi-level control policy directly from the historical data? So for this, we try to use offline RL, where again the goal is to try to eliminate the need of online learning. So therefore eliminating the need of interacting with simulation environments and learning directly from historical data from the real world. So in this offline RL framework, we essentially assume that we have some behavior policy. We call this pi beta, that is interacting with environment and collecting data. And this pi beta could be, for example, some heuristic or some optimization method. Doesn't need to be an RL-based policy. But it is interacting with environment and it's collecting data. And based on this data set, the goal then with offline RL is then, can we learn a policy pi that can be at least as good or hopefully better than the policy that was used to collect the data, so our behavior policy, that we can then take out and deploy in the real world, and that should hopefully get us to a good starting point. Then maybe we may need a little bit of fine-tuning or an interaction with the environment to just fine-tune it a little bit, optimize it a bit more, but But the idea is that we can have a very good starting point for our policy. So this is what we're trying to do. And well, can we just use online RL algorithms? And the tricky thing here is that online algorithms, of course, they assume that they have access to an environment that they can interact with. So they assume the access to online interactions to essentially correct erroneous estimates. And this is really challenging if we try to do this offline, because offline RL algorithms, they simply try an action, or they know what it, from historical data, right? They know what the cost and or the reward of that given action in a current state. So they don't know if a given action that was never seen before, and you start going, let's say, out of distribution, we don't know whether that was a good and bad action. And that essentially sort of takes us out of distribution, creates problems for the offline RL. So essentially, these offline RL methods are trying to account for unseen and out of distribution, let's say, actions, while essentially allowing generalization to behaviors that are better, or hopefully better, than the behaviors seen in the data set. So what they essentially try to do is to find the best behaviors in the data set and try to generalize from these best behaviors to similar situations, essentially trying to stitch together different parts of good behavior to hopefully come up with an even better behavior policy. So if you just try to apply this directly to our bilevel framework, and using this is again for the AMOD control problem that I was mentioning before. If you try to apply this directly using some historical data. So in this case, what we did was to train the reinforcement learning agent half the way, let's say. So it was still quite bad, not nearly perfect. And we were using this half-trained agent to collect some data. And we collected some data, and then we just used off-the-shelf, offline reinforcement learning algorithms. So in this case, we're trying to use something called CQL, conservative Q-learning. And if we try and we feed this data from the half-trained policy into a offline RL algorithm, we can see that it actually seems to perform quite well, close to online methods. So here we are comparing with our soft architect agent. So this was our online learning-based controller. And we saw that offline we can actually get fairly close to the online methods. So they were thinking, yeah, great, we are close to the online methods, and we gained up to 20% of sample efficiency. So this is great. These things are looking great, but the problem is that here, if we are, while doing this, we are assuming that we have access to essentially the upper level action. So the action of the upper level controller in the bilevel policy structure. So in our bilevel policy, remember again, we have the RL agent deciding the desired distribution or the desired next state, and then we have a lower level control that then tries to achieve that desired state. So if we have access to so if our behavior policy also had the same structure and we have access to the actions that were taken by the higher level policy, then we can just apply off-the-shelf offline RL methods on these actions from the upper level controller to just try and learn it offline. But the thing is that in reality, this is not available. For most real world problems, what we have is data from the lower level controller, right? Because this is what is observed. So in the case of the AMOD rebalancing, what the data would contain is actual rebalancing movements between the cars, not actions from an upper level control. Actually, the policy that was used to collect the data may not even be hierarchical, right? It could have been obtained by using some heuristic or some optimization method. So the question is then, can we learn a bi-level policy offline from the observed data from the lower level actions? So these, essentially what we're trying to do here is to learn, still learn a hierarchical policy structure, because we saw the advantages that is provided, I described in the previous slides. So essentially you want to have some higher level policy controller, RL based, and then some lower level controller that, given the upper level action, essentially tries to find the lower level action that best tries to achieve the desired state, mu. So essentially what we need to do offline RL is to have some high-level dataset, what we call a high-level dataset, which is a dataset of state transitions that includes the upper-level action, so the action taken by the upper-level controller. So if we have these, then great, then we can just use an off-the-shelf offline RL algorithm to then learn offline our upper-level controller, and we can use it, still use it in a bi-level framework. But the thing is that in reality, in most problems, what we have is low-level offline data, which is, rather than including information about the upper-level action, it only contains information about the lower-level action, right? So in this case, the rebalancing movements of the columns. So what we proposed was what we call offline hierarchical RL via inverse optimization, or Ohio for short. And the way it works is the intuition is rather simple. So what we try to do is, given this lower level offline data, we try to solve the inverse problem, essentially trying to find the upper level action mu that would have led to the observed action A. So let's look at what an overview of this framework looks like. So we have some offline trajectory data, and these may contain states and actions, or actually could also contain just states and also the rewards associated with those state transitions. And what we try to do is to essentially solve the inverse problem, to then figure out what was the actions that, from the upper level policy, that most likely would have generated these lower level actions that we observed in our data. And then if we have this high level data set, we can then plug it into an off-the-shelf offline RL algorithm, or even behavior cloning. We saw that that was performing quite well as well. And then once we have this, we can train our agent, and then at inference time, we can still keep using our bi-level framework, where we have upper level action from RL-based controller fed into the lower level controller that would then determining the lower level action. And we propose to do this in two ways. So we have two settings, let's say. So the first one is where our offline trajectory data contains both states and actions. And if the data set also includes the lower level action, then the way we propose to do this is by essentially solving a maximum likelihood problem, or a regularized maximum likelihood problem. What we try to do is to find the upper level action U that maximizes the log probability of our policy. So the probability of the action, the log probability of the lower level policy. Right. So it's the probability of the lower level action given the state and the upper level action. So we're trying to find the value of the upper level action that maximizes this log probability with some regularization term. So this is essentially becomes a regularized maximum likelihood estimation problem. It's also possible, so more generally, we can also try to solve this for a case where our trajectory data doesn't contain actions. So it's also possible to do it even if our data set of offline data only contains states. So in this case, what we require additionally is to have access to an approximate dynamics model. So we need to have some approximation of the environment dynamics. So essentially, we need to have an approximation for the probability of the next state given the current state and the action. And the idea is essentially to try to leverage the model information locally in time to solve this optimization problem. So here we are essentially trying to find the upper level action that maximizes the log probability of the next state, given that the action is given by the lower level policy controller. So we then tried out this Ohio approach, and we compared it with end-to-end offline RL. So here we are seeing, well, we're seeing multiple things. So if we focus, for example, just on the offline RL methods, here we are considering two offline RL off the shelf. So this is IQL and CQL, so conservative Q-learning and iterative Q-learning. And we are comparing this with in our Ohio framework, where we solve the inverse problem to then obtain the upper level action, to then plug it into our lower level controller, versus doing this end to end. So trying to do offline RL directly from the lower level actions. So in this case, no, without having a bi-level policy structure, essentially. And we can see that while this doesn't really work very well, doing end-to-end, if we use the Ohio framework, we can learn bi-level policies that work quite well and relatively close to, and this again is showing reward values, and again quite comparable to the values obtained by the online RL approach. Again, if we compare just online with online, so online end-to-end also doesn't work doesn't work well at all. Whereas if we use the bi-level approach, this seems to work much better. But most importantly, the message is if we use offline RL with the Ohio framework, solving the inverse problem, and keep using the bi-level framework, this seems to work much better than doing end-to-end offline RL. And also, if we use just behavior cloning without using offline RL, we see that this performs quite well under the Ohio framework for solving the inverse problem. So the takeaways are essentially that the Ohio framework significantly outperforms end-to-end approaches. We saw that the hierarchical framework again significantly improves scalability and robustness. So one thing that I didn't show in the slide, but we saw that the policies learned by this Ohio approach is much more robust and was also ensuring domain constraints, which the end-to-end approaches were struggling quite a lot with. And the other thing that we saw that was that this was also quite sample efficient. It was also possible to do some of online fine tuning to then fine-tune, optimize the service a bit more. And this, therefore, basically we were starting with a much better starting point than if we were to just, start from scratch and essentially avoiding expensive rebalancing decisions in the beginning when the agent is not, still has a bad policy. So just to finalize two quick more messages is that this approach actually, if you think about it, is actually quite general. So that's one thing that we realize is that this can actually be used beyond transportation. So one thing that we realized was that, well, these bi-level or hierarchical RL approaches are quite common, for example, in robotics, where you have lower level controllers determining the actual movements of, let's say, robot arms and things like that, where you have high-level controllers determining sort of goal states. So since this is a relatively common approach in robotics, we started trying out to explore, well, what are the possibilities of Ohio in solving robotics problems. So I'm not going to go into detail because I think it's a bit outside of the topic, but But quickly, what we saw was that Ohio was essentially able to successfully recover the hierarchical policies from datasets collected by non-hierarchical behavior policies. And then we experimented with different ways of solving the inverse problem. We were doing both analytical inverse and also numerical inverse. We saw that the analytical inverse was more susceptible to model error and model misspecifications. But essentially, the message is that we found was that even in this in these robotics applications, we saw the offline, the Ohio approach work much better. Whereas if you were to do this end-to-end, or at least comparable with end-to-end approaches. Yeah, so this is just experiments for a different type of robotics manipulation problem, where again we see that the Ohio approach outperforms the IQLs. So standard end-to-end RL versus the Ohio approach with the bi-level framework policy structure. So to conclude, we have introduced a bi-level framework to handle general network flow problems in transportation, and more broadly, we also saw other applications. The framework essentially consisted of two steps. So in the upper level control decision, we were specifying the desired outcomes through an RL agent. In the lower level controller, we were solving a linear control problem to achieve, or as best as possible, the desired outcome. This framework essentially tries to combine the best of learning-based control, so the capabilities of handling nonlinear dynamics, stochasticities, and all the scalability advantages, with the advantages of optimization-based methods. So the fact that there's no need for training, for example, and the capabilities of ensuring constraints. We demonstrated this application for AMOD rebalancing and pricing problems, and also for inventory management, and also very quickly some robotics for the robotic applications. We saw that they achieve close to optimal performance while being significantly more sample efficient and ensuring domain constraints. And we also saw that these policies tend to be quite robust, and they tend to generalize very well to new scenarios. Yeah, thanks both to the hierarchical bi-level framework and to the use of graph neural networks, and even better with meta-reinforcement learning. And then lastly, we proposed Ohio, which was a framework that leverages the structure of the lower, or tries to leverage the structure of the lower level policies to combine hierarchical or bi-level with RL with offline RL. We saw that it successfully recovers hierarchical policies offline from datasets generated from arbitrary behavior policies, and it clearly outperforms, significantly outperforms offline RL, both in terms of well, performance and robustness, by the fact that it can directly encode domain-specific constraints. Yeah, so that's it for me. Just a last message is the thank you, because this work was done by a very big, rather big team of contributors. My PhD students, Daniele, Caroline, well, Xinling was also a student here as well at some point. James, Kaidi, Francisco, and Marco, all key collaborators for this work. It will not be possible, certainly, without them. Actually, they did most of the heavy lifting on all of these. Yeah, that's all from me. Thank you.
Thank you. Thank you, Philip, for the great talk.
Thank you, Xinling.
I'm first. Okay. Yeah, Joelle needs to leave for a PI meeting, so I'll be hosting the QA session. Yeah, but that's very rich set of work as always. Like I was really enjoying working on this topic during your master thesis. So I think now we will open the chat to the audience. So if you have any question, you can type in the chat, or you can just unmute and ask. Yeah, so feel free to ask if you have any.
I have one question or two. Up to how many nodes can this framework scale? Like, what is the maximum number that you tried?
Yeah, I think the largest we went was like a 20 by 20 grid. for the MOD problem, for example. I think
20
that's,
by 20, so 400 in total,
yeah.
or 20?
Yes.
Okay, yeah.
Yes, exactly. And this, if you apply a grid like this to an area like Manhattan, it already gives you rather small zones. So we were debating whether it makes sense to consider even smaller zones, but it's not like we didn't try because we don't think it could achieve it. I mean, yeah, scalability wise, I think it would still be able to go. We stopped because we thought from the domain perspective it wouldn't make sense to go below this, but yeah.
And then the output distribution that the reinforcement learning agent outputs, it's actually over 400 graphs, nodes. So
Yes.
it's like very tiny numbers that
Yes.
you receive.
Exactly. So I didn't cover the details, but essentially, yes, the reinforcement learning agent will be, in this case, will be over 400 nodes, a distribution. So it will be rather the small numbers, and the way we parameterize the policy is actually with the Dirichlet distribution. So we have the neural network, the GNN outputting one value per node, and this will be the parameter of a Dirichlet distribution over all the nodes, so over 400 nodes. Yeah.
And if you like refine the regions even smaller, like make them more detailed, could also the Oracle policy perform better? Or is that already at the maximum independent of how you choose the regions?
Potentially, yes. Yeah, I didn't. Yeah, I never thought about. Yeah, yes. If you, I guess you could try to optimize the way you partition the city in a way that you make heuristics, even heuristics, perform better. And actually, yeah, we try to use an approach. So, for example, the way we partition the cities, we try different ways. Oh, sorry, I went backwards. Oops. We try different ways actually of partitioning the cities. Some of them we did a grid partitioning, others we partitioned based on travel times. So we try to partition the cities such that travel times within each area are sort of similar. So we did essentially a graph cut clustering based on travel times to try to partition the city in a way. But I
Yeah.
guess you could come up with a clever way of partitioning the city that would make the Oracle perform better. But you will still face scalability issues, right? Because that's independent.
Yeah.
Yeah, that's independent of
Yeah,
the.
like I guess computation times will go up by quite a lot, but maybe potentially it can find like even like more quality solutions. Because I guess if you like group a lot of agents in one area, then you lose some information of detail.
Yes. That's definitely true. Yeah. So the overall performance of the system would certainly be dependent on the way you partition the city, having the right partitioning. Yeah. Matters.
Yeah, very nice. Thank you very much.
Thank you very much.
Any other questions? If not, I think, yeah, we are quite on time, like 1 minute before talk. So yeah, thank you again, Filipe, for giving this great talk, and catch up soon.
Thank you very much. Looking forward to it.
Thank you.
Yes. Thank you all.
Ciao.
Bye bye.